Alright, today we're going to be solving Griffiths problem 2.13. We're going to be finding the electric field contributions from the following charge distribution. So in Griffiths 2.13, essentially what we have is this continuous charge distribution along a straight axis. In this case, I'll define it as the z-axis. Here we'll have x and y, and this is lambda here. So in other words, we can say that the charge distribution in all space, x, is equal to nothing but the scalar field, denoted as lambda times delta x, delta y. Okay? We can do this because essentially this states that for the set of all real numbers, this scalar field will only be non-zero if it's along the x and the y axes that are 0, which is simply the z-axis. And so this is a neat little trick to use this delta basis to essentially set a set of points that are not 0. So using this approach, we can use Coulomb's law. And this is one way to do this. You can do this using Gauss's law, which we'll do in another video. So we can write down Coulomb's law as 1 over 4 pi epsilon 0 times the integral over all space, charge distribution of x, separation vector, and then magnitude, and this forms the unit vector, and then we can area over all space. Okay. Nice. So we can now essentially use this Coulomb's law and solve it. So the first thing that we need to do is apply the delta function. We'll have a neat little kind of thing. We can just say that the integral over a delta function times the function with respect to a scalar variable is just equal to that function by itself. And so if we can make this function a multivariate function, and in that case we'll have nothing but g of 0 y z. So continuing, we'll have 1 over 4 pi epsilon 0 integral lambda delta x prime delta y prime, right? dx prime, dy prime, dz prime, and then I forgot the separation vector, and the magnitude. And so essentially these two delta functions cause all of the y prime components in these two things to disappear. So absorbing all this into some constant, we can now write cleanly that the total vector field is given by these constants multiplied by the integral. I'm just going to set the bounds beforehand. Separation vector divided by, now I'll write this magnitude explicitly, x squared plus y squared plus z minus z prime squared, 3 over 2, and then we can multiply by dz prime. And we can use this property here with this to show why that's true. Okay, so this is actually quite simple because of the little fun fact I threw in earlier. Before we continue, let's set x equals to this thing, and y equals to this thing, and then z equals to z. These are the typical cylindrical coordinates. Okay? And then we can continue. So I'll set this aside and we'll return to this as I write. So the next step is to write down each component. So I'll start with the x component here. So this is equal to lambda. We're going to have simply x. So from this, the numerator of this will just be like x minus x prime. It's going to be a vector valued function. It'll just be x, y, z minus z prime. All right. So this here will just be given to x over, I'll just write down the magnitude to save space. And then we can, substitute this out. And then if we use that definition I used earlier, we'll just get r squared plus z minus z prime squared. 3 over 2 dz prime. Okay. Then we can write down, we can say that u is equal to z minus z prime, which gives us that du is equal to minus dz prime. So then Ex is going to equal to lambda r cos theta integral 1 over minus 1 actually r squared plus u squared 3 over 2 du. Okay, so now this is a standard integral, this one right here. So if I more or less want to solve this, I can perform the following substitution. I can say that let's denote a new variable v, and this v is just going to equal to r multiplied by tangent of u. Okay, so this here is defined as a tangent, so that just gives us u is equal to arctan v over r. And similarly, we can say that du is equal to du is equal to r times secant squared of u. Sorry. Yeah, no, this is correct. V. dv. Okay, so du is equal to r secant squared v dv. And so long story short, this integral becomes r cos theta, the integral of 1 over r squared multiplied by secant of v. dv. Okay, and so now we can simply cancel this out. Integral 1 over secant is simply cos v dv, and this gives us lambda cos theta r sine v. Okay, and now we can, well, this problem is essentially solved, right? We can do one more interesting thing, and evaluate this from the bounds minus infinity to infinity. And this is nothing that's unsolvable. Essentially what we can do is we can retransform the variables. We know that v is equal to arctan of u. Plug that in, and essentially the final answer that we get is this cos theta over r multiplied by the number 2. So this integral becomes 2. Okay, and so what do we get is that Ex is nothing but gamma, or lambda, cos theta r times 2. Similarly, by symmetry, we get that Ey is equal to lambda sine theta times 2 over r. Okay. Lastly, we can quickly solve for the z component. Oops. Ez, and this is nothing but the integral between z minus z prime over this displacement. I'll just write down the displacement in full just for fun, just to show it, to prove a point really. And what we can do is we can take a look at this in terms of functions. We can define f of z prime equal to z minus z prime. This is an odd function. And we can define 1 over as g of z prime, 1 over the displacement cubed. And we'll note that this is an even function. This even function comes from the fact that no matter what value z prime takes, the denominator of this will always be equal to a positive number. And so a positive number raised to whatever power will be positive, which will give us some positive thing on both axes. And so the fact that we're integrating this over all space gives us an odd function times an even function. And so an integral over an odd times even is just equal to 0 due to the property of it being odd. So we can just simply state that Ez is equal to 0. Okay? All right. So now we can take a look at this final E field. So this is going to equal to lambda over 4 pi epsilon 0 multiplied by 2 over r, and we'll have cos theta sine theta 0. So this will cancel 2, and we're left with that E, due to a line charge, is just equal to lambda over 2 pi epsilon 0 times r cos theta sine theta 0, and this is in the Cartesian basis. Okay, so this is in the Cartesian basis. If we want to, for example, turn this into the polar basis, we can use a rotation matrix, but this kind of makes very simple sense. And so we can even transform this back and just recall that we said that x is equal to r cos theta and y equals to r sine theta. So we can essentially multiply this by r, and we'll get that E lambda is equal to lambda over 2 pi epsilon 0 r squared. And now we can use the fact that r times this and this, x, y, 0. Yeah, that seems more or less correct. Okay, and what do we need to consider about this? Well, if we're away from the line, the only things that matter is the square distance, which will just become r, so that the magnitude of E at all points is just equal to lambda over 2 pi epsilon 0 times r. So this is the magnitude in all space, where r is the distance from this plane here. And what's the other thing? When we set x and y equal to 0, we're actually going to be situated on the point, on the line here. And you'll notice that this electric field diverges. So how to kind of mitigate that? Well, we can recall the definition that we used. We used the delta basis here. We used the delta basis for the charge distribution. And so we can actually use Gauss's law, for example, for a cylinder to find out what the charge should be as we reduce our Gaussian surface to 0. So I can quickly do that here. So by Gauss's law, we can say that E dotted by some thing would equal to the charge distribution over epsilon 0. So for a Gaussian kind of pillbox like this, or like this little cylinder, we can say that the surface area would be nothing but the distance. So it's just going to be the surface is coming out from here, and using using essentially this area here, we can do that. So for this, it would just be the circumference times the length. So E would be constant, so it comes out, and then this would be 2 pi r, which is the circumference, multiplied by L, would be equal to the total charge, or lambda times L over epsilon 0. And we'll see that E is equal to lambda over 2 pi epsilon 0 r. And so recall that these are delta functions, like essentially as we get closer and closer to this line, we should eventually hit a diverging thing. But we know that using this Gaussian thing, we'll have this kind of form. So we can take the limit and whatnot if you want to be pedantic, but it should be more or less equal to the charge distribution over this coefficient. Yeah, so that's this problem solved in 2 ways, and we can go through all the pages one by one for a quick review. So, starting off, just go through this here. So please pause and review if you need to.